in this talk. So I will start with transcendental number theory, and I start from the very, very beginning, from a theorem by Liouville, which allowed him to construct a first example of transcendental number. So theorem says, just in case if anyone missed it at the time, if you have an algebraic number of degree n, then for a certain constant which depends on this number only, the number alpha can't be approximated by a rational any better than C alpha divided by nth degree of the denominator. So, for example, in order to prove that a number is transcendental, you can just try to construct an infinite sequence of very nice approximations to this number. So this is a first example which was proved by Liouville to be transcendental. Here, basically, to construct a sequence of rational approximations, you just carve this infinite series at position n, and you find a sequence which generally shows you violate this inequality. Later, it appeared that, in fact, this theorem is unapplicable to almost all transcendental numbers. In fact, numbers for which you can apply such a theorem are called now Liouville numbers, and they are known to have measure zero and dimension zero, the set of these numbers. In the same article where Liouville proved this theorem, constructed this example, he discussed possible extensions of his method. Well, he constructed some other examples which we will not discuss today. However, he discussed as well these two examples. These series are just very lacunary, but slightly less lacunary than this one. If you try the same trick, just cut this series at position n, what you find is not good enough to show the transcendence with Liouville theorem. It is enough to merely to show the irrationality. So, however, well, approximations which you get just by truncating infinite series are not enough even to show that these numbers are not badly approximable. Well, so after the work of Liouville, among many other problems, there remained a problem what to do with these numbers. Finally, both of them were proved to be transcendental, actually both with Mahler's method. This one directly, it was in the very base of the Mahler's method. This one by a very indirect application of it. Well, in fact, I want to discuss the proof why this number is transcendental, just because I think it is instructive in understanding why one emergent problem in dynamics is linked with a problem in algebraic independence. So when Mahler proved his theorem, notably that this number is transcendental, he proved at the same time, just by the very same method, that if you consider such function, you just put z in place of 1 over 10 here, this constant. This function takes transcendental values for all algebraic alpha with absolute value between 0 and 1, and of course different from 0. Okay, just very briefly, recall the proof of this fact. Well, briefly, it means it will take 10 minutes, I think. Basically, it is pretty elementary. You just need two facts. One is a slight generalization of Liouville inequality. You have, this is the fact that for any polynomial in two variables, and for any two algebraic numbers, which belong to the same number field L. Well, in purposes of theorem, it will be always the best choice to take simply a field generated by alpha and beta. We have the following inequality. continue in a moment. This is sum of Archimedean absolute values of coefficients of P, so-called length of P. So just to accelerate, I do it very quickly. This notation. So further we have to subtract degree of P and X and degree, because you have to multiply by a height of alpha and do the same with the second variable. A small exercise, if you didn't do this, deduce a usual Liouville inequality from this one. A second fact which we will need is just a small application of linear algebra.
So what's h?
Good question, thank you. Actually, h is a logarithmic height. Well, it's not extremely complicated to define, but I prefer to avoid it. I just give a list of properties. So first of all, if n is, say, a natural number, then height of n is logarithm n. This is property 0. Two other it behaves well on the multiplication and the sum of the numbers. One property we will need in further calculation. Thank you for asking this question. Is that if you calculate the product of two numbers, the height of the product is the sum of heights. In particular, h of alpha to the power n, say bits, equals to n times h of alpha. And point B, well.
Can I ask a question? So I would think of the logarithmic height of a rational as being log of the maximum numerator denominator, and it doesn't have this property, this multiplicative property. So what?
It is logarithm of this. This is why it is logarithmic height.
So it is the average of the logs
so what's the height of a
p-adic
half?
basis.
What's the height of a half?
Logarithm 2.
And height of 2 is log 2.
Yeah, exactly.
And height of a half times 2 is not twice log 2.
Yep.
Right.
Right. Thank you. So, okay. However, we have this property.
I'm awake.
Okay. Now check this property. If you calculate the sum of n numbers, it does not exceed the sum as well. However, it is not true in this addition. We have to add logarithm of n. Okay.
Excuse me, for the first property, don't you need an hypothesis that P alpha beta equals 0 or not?
P alpha beta. Yeah.
No, log of P alpha beta.
Yeah, the polynomial is identically 0.
Yeah.
Say again.
So if, for example, I take a polynomial x minus y,
Sure. Yeah. Okay. Yeah. Well. Side Z, P of alpha beta is not 0. Yeah. Okay. Okay, second fact, which we all need, is that assume we have a function. Actually, it will be this Mahler's function, sum of z to power 2 to the power n. But let f of z be even a formal power series. Then for every n, there exists a polynomial Pn such that it has a very big order of magnitude at 0. There will be second property of Pn about degrees. Well, it is a certain constant z to mu of n plus O big of z mu of n plus 1. And okay, well, degree in both variables of P I at most n, and this order of vanishing is at least n squared. Well, this basic exercise in linear algebra, when you develop all these in formal power series and make matrices of coefficients. Okay, now how we prove our theorem? We take, we take some n big, later it will be sufficiently big number, and substitute there alpha to the power 2 to n small plus 1. This is another sufficiently big number. How big? You will be able to specify it like that. Well, plus O big, but well, just to simplify the notation, I double the coefficient here, and I erase this O big. Well, again, to precise a small theme, see, you're very attentive. I assume I can always construct P in a way to have C to be strictly positive.
What is the power of the big O of n or square root of n?
It is a certain nu of n. Well, basically it is n square, but I can't exactly say that I will have non-zero coefficient with n square.
All these letters are new.
It is new. Yeah. Is it better? Okay. Well, again, later we will just one step later we will have lower bound for logarithm. So I apply logarithm here. Logarithm of all this stuff, the same as here, is upper bounded by logarithm 2c plus v of n times 2 to n plus 1 times logarithm alpha. Actually, it is a negative term because the absolute value of alpha is less than 1. Actually, one remark, it is a huge negative term because this is approximately n squared. Well, the last step, and we finish with this elementary proof. Well, I need everything I have on board. Well, I erase the properties of the height. You just remember you can do essentially everything with it under the control of Francois and Thomas. Okay. I just want to apply this lower bound to this polynomial. Actually here it is a point to assume that what we try to prove is not true, and assume that both simultaneously alpha and f of alpha belong to the same number field L. Well, and alpha is non-zero. Okay, I straightforwardly use this in small remark. If f of alpha belongs to L, then sorry, I forgotten to say one important thing. Up to now, all this reasoning works perfectly well, essentially with any analytic function f. From this moment on, I want to restrain myself to consider the function f of z, which is the Mahler function. It satisfies this functional equation, which is the key to the proof. And applying it recursively, you find that if f of alpha belongs to a number field L, then f of alpha to any power n, that's equal to 2n plus 1, belong to L. So finally, we can apply this lower bound to a number alpha to 2n plus 1. This is one my algebraic number. This is another my algebraic number. Well, this absolute value. No. Okay, here we find minus this constant. Actually, it's not important, so I put Cn times L of Pn minus degree of Pn is upper bounded by n. So I subtracted most n times height of alpha to 2n plus 1 on top of this. And here I have to put f of alpha to 2n plus 1, but I can recursively apply well, the upper bound, the properties of logarithmic height I have just erased. So I will have here f of alpha, height of f of alpha plus the sum uh, 2 to k, which again gives me 2 to k here. And basically, this term is approximately, roughly speaking, the same as this. Well, I rewrite it one more time. I will have one constant with the length of my polynomial minus n times 2 to n plus 1 times the height of alpha. Well, n plus 2 if I take into account this term. 15 minutes. Okay, now the claim is that for sufficiently big, and when you fix n big, you can always choose this n small, such that say, this negative term, this negative term in absolute value is bigger than any term you can find here. Basically, because here you have n squared times 2 to n plus 1. Here, choosing wisely n small, you can always kill this term. And otherwise, with n squared, you kill both these terms. That's all. Okay. Now let's leave this proof for a moment. Do you have a button to? Okay. Let's continue this presentation for a few moments. Well, of course, the same proof works if you try to substitute z to the power of d instead of z squared. The same ideas, but well, slightly more complicated calculations can show you that if you consider this system of functional equations, you still can prove the same kind of result. For example, if all these functions are algebraically independent, then at algebraic points different from 0, they take algebraically independent values. If you know that there is only one relation between them, in algebraic points they take such values that there is exactly one relation between them, and so on. I will return to this theorem later. For a moment, let's just skip quickly to application in computer science. Just short remark. Well, it's unimportant. Say you can do something even more complicated. Instead of substituting z to some power, you can substitute essentially any polynomial with the only condition that order of vanishing at 0 of this polynomial has to be at least 2. Then you have the same kind of results. Well, further you can substitute rational fractions, and there are plenty of results, but actually further results depend on a certain problem in algebraic dynamics, to which I will return at the end of the proof. Now I think we need a certain distraction, a break from all this boring stuff. Just what can we do with this? Let's switch topic to theoretical computer science. In fact, surprisingly, these weird functional systems encode some information about some class of Turing machines. Again, I start from the beginning, from the work by Turing on computable numbers. Yes?
So, this logarithmic height is the line to the Archimedean or non-Archimedean norm. So, is it crucial that you use Archimedean norm for alpha?
No, no, you can use either. No. Well, to be very, very careful, I would check one more time, but in principle, it should work the same. Well, normally this estimate never depends which place you choose. Okay, well, so Turing presented a concept of computable numbers, basically numbers which can be computed with so-called Turing machine, or with any computer, maybe with infinite memory. Slightly later, Hartmanis and Stearns published a a famous article on the computational complexity of algorithms. They told, okay, there are computable numbers. These are the only numbers which we can compute, well, conjecturally by any means. However, they can be one computable is different from another computable because, for example, a number 2 or 2 over 3 is something we have in hand, which takes no time to deal with. At the same time, if you take, say, pi or something even more weird, calculation with such number is something more time-consuming, work involved. It's not that straightforward as working with just number 2, for example, with a rational number. So they introduced this classification of algorithms, which is used widely now, for example, to compare multiplications algorithms between them, or crypt algorithms, and so on. I will introduce the definition slightly later. The one remark, they worked not with the very classical Turing machine, they allowed their machine to have multiple tapes. It changed slightly the situation, but I'm not expert in computer science, so I just know that classification was with one tape machine is not exactly the same as classification with multi-tape Turing machine. So I want to mention this. And the complexity is of course that we take a function. Actually, this T of n will be either n or n squared. We'll never consider even such complicated function as exponential. And well, computable is not restrictive condition for us. All we want it to be increasing. And we say that a sequence, say alpha, is T computable if we can construct a Turing machine, a multi-tape Turing machine, such that it can produce first n digits of our first n elements of our sequence in time T of n. The class of T computable, say decimal sequences or any sequences, we will denote by S of T, and a number has complexity T or belongs to the class ST if its decimal expansion has complexity ST. That's all we need at the moment. Well, Hartmanians and Stearns experimented a little. Well, they proved a number of very nice theorems, but at the moment, in this talk, they are not important for us. They started various concrete classes of numbers. For example, a rational number clearly belongs to the class Sn. You just produce a machine which prints pre-period and then recursively prints the period. They show that algebraic numbers belongs to the class Sn squared. But after that, they observed that, for example, if you consider Liouville constant, then it again belongs to the class Sn. If you consider this Mahler's constant, say it belongs to the class Sn. And actually, there are plenty of transcendental numbers which belongs to the class Sn and not to Sn squared. That it was the year 60s, so well, for one reason or for another, such situation appeared to be slightly counterintuitive to them. So, well, they just started to look at least, what appeared abnormal for them is that normally algebraic numbers are considered as simpler than transcendental numbers. So they started to look for at least one algebraic number which belonged to the class Sn. And they didn't succeed. Actually, nowadays we believe that there is no algebraic numbers which can be calculated in linear times. This was the initial problem set by Hartmanians and Stearns. And what is called by conjecture Hartmanians and Stearns nowadays is that there is no algebraic number apart from rationals such that they belong to the class Sn. Well, now I explain at the same time two reasons why I think this conjecture is interesting and important, and why it is reasonable to believe that indeed this conjecture holds true. Well, one application, if you play a little bit with Newton method, you will show that if fm of n denotes the complexity of multiplication, then you can calculate an algebraic number in the time m of n. Just calculate first n digits of an algebraic number has the same complexity as just multiply two integers having at most n digits each. Well, in fact, this is quite the complexity of multiplication is important for theoretical computer science because multiplication is involved in most of algorithms, at least in most of crypto algorithms. People all the time try to find somehow quicker and quicker algorithms for multiplication. The current record for this is, as far as I know, something like n logarithm n double logarithm n. Just write that more. people who study these algorithms suppose that the lower bound for the complexity of multiplication is n logarithm n. Hartmann-Stern's conjecture doesn't really provide this lower bound. However, it is a weaker statement that, well, m of n, it's not exactly bigger than n, but the complexity is bigger than n. More or less, it is in the same spirit as this lower bound, slightly more complicated than n. Well, another reason why this conjecture is interesting is that okay. There is this meta-mathematical question how random is a decimal expansion of algebraic number. There is a conjecture by Borel that, say, if you take decimal expansion of square root of 2 of any algebraic number, if you fix any pattern of digits of length k, then this pattern asymptotically will appear in decimal expansion of your given algebraic number with the same uniform frequency, 10 to the power minus 1. Most often people studying this conjecture say that if you show that a number is normal, then we will show that decimal expansion or any expansion to any base of algebraic number is really random. However, normal is just a weak test for randomness because there are some funny numbers, plenty of them, something like 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, you know next digits, 12. I mean, any computer and any man can produce it in linear time. Such numbers are known to be normal. In fact, there is a huge family of them. Well, you can list primes or anything of this kind. There is very nice article of Rajesh on this topic. Actually, these are far from being all the examples of this kind. They all are normal, but they are far from being random. You definitely can say always what is the next digit you have to write. At the same time, the complexity of calculation of decimal expansion is something which really corresponds to the intuitive understanding of randomness. If you can't quickly provide the next digit, well, more or less it is random. At least it corresponds perfectly to the purpose which is required from random sequences in different computer systems when you produce random passwords and other things. Well, as far as I know, the problem on this conjecture of Borel on normal numbers is very far from being solved. In fact, much weaker question, just to provide one example of a concrete algebraic number of a concrete base, at least 3. For 2 it is trivial, and a digit in this base, such that in this example, your given algebraic number has infinitely many occurrences of your given digit d. I mean expansion of alpha to the base b. It is still an open problem, and as far as I know, there are not too much progress to this. At the same time, there is a progress towards Hartmann-Stern's conjecture. Basically, it is still open for general Turing machines. However, you can do a trick. I'll show it on this page. Well, you can simplify problems so that you can solve it. Basically, you can remove the memory. You can remove all these tapes where you maybe save your intermediate results. When you remove memory from Turing machine, then you find what is called finite automata. Finite automata, as I've told, the Turing machine without memory, just finite number of states. Here there are just 2 states, S0 and S1. You have a certain transitive function. At every moment you receive certain input, and then according to this input and your state, you move along the given arrow. So to produce, well, now we try to apply such very simple machines without memory to produce certain sequences. Presumably, here it will be binary expansions of certain numbers. The convention is that to produce the nth term of our sequence, we construct the input for this automata. We just take n, take its binary expansion. In general, it will be expansion to the base, the number of states that our automata has. And, well, just every next moment of time, we send the next digit. It's much easier to, okay, I'll try to draw it here. So, for example, at some point, you want to calculate this 2 plus 8. If I'm not wrong, it is 25 in this expansion. You want to calculate 25th term of the sequence encoded by this finite automata. What do? You start always at position as 0. You read 0, you stay here, then you...
Whatever that number is, it's even.
It is, so it is 26. Sorry. Yeah, it is. Just forgotten that I start not from 1. Yeah, again, then we calculate 26th term of this sequence. We start with 0. We remain, well, we start from position S0 and we read the first symbol, 0. So we stay here in S0. The next symbol we read is 1. So we move along from S0 along this arrow to S1. There we read our next symbol, 0. We stay here. Next we read 1. We move here. Next we read the last symbol of the input 1. So we return here. So we stop the last symbol after we read the last symbol. We arrive to the state S1. We stop here. We read what we have to write down here. We write down B. Well, if we are interested in the next element, 1, 1, this binary expansion, then the first symbol we read is 1. So we move from S0 to S1. Next we read 1. We return here. Now we're here. Next symbol we read is 0. So we just move in this loop. Next symbol is 1. We move here. And the next symbol 1, we return here. So we stop at position as 0. We write A, and so on. 26th position, 27th position, something else from this. In fact, for those who know this, if I'm not, at least I try to put here the automata corresponding to 2 or more sequence. Modulo an error from my part, it should be it. It should produce a 2 or more sequence. Well, for this just remind of formal definition. Basically, you have a finite alphabet. For us, it will be just all the decimals in Q, expansion to base Q. It has a finite number of states S. You precise a certain initial state. Here it was a 0. Delta is drawn by these arrows, transitive function. And tau output function, it just prescribes what symbol we have to write down if we start in the given state. Well, at some point when it appears that apparently Hartmann-Stevens conjecture is quite complicated, they try to study only Turing machines without memory, the finite automata. You can ask the same question. Is it true if you take any I'm sorry, it is a typo, of course. You're interested. You're interested in alpha, which belongs, well, which are irrational, and you are interested, basically, take such that alpha is automatic, that to say its decimal expansion can be produced by a finite automata. Is it true that alpha is not algebraic as well. Oof. However, this simplified conjecture, please try to imagine there is no bar here. It is just simple Q. I mean, a rational alpha. This conjecture was quite hard to study. For example, it was studied by van der Poorten. Well, I'm very bad in names. Well, basically, there were quite a lot of researchers working on it, trying to do something. It was even set up by van der Poorten models a technical condition. However, he wasn't able to remove that condition. Finally, this theorem was proved by Adamczewski and Bougeon in 2007. It appeared that indeed this is true, at least for Turing machines without memory. In this proof, Adamczewski and Bougeon used Schmidt subspace theorem. Well, a certain ineffective result from number theory. However, for some reasons, it is not the best. Well, it is nice to have to settle up this theorem, but for generalization, it's not the ideal solution because these arguments were quite hard to generalize for further use for more complicated machines. A more regular way to treat this conjecture about finite automata at least is to refer to these strange functional systems, Mahler systems, which we have seen in the very beginning. In fact, it appears that if you have a real number such that it is automatic, it's for decimal, say, expansion can be produced by finite automata with Q states, then we can find function which will basically this function will be a solution to Mahler type functional system of equation. You can produce this alpha simply by taking appropriate system, you construct it somehow, and then alpha will be a value of f1, for example, at 0.1/10. Again, I want to show this link. This time it should be simpler than this calculation with Mahler's method. It is basically it is just summation by packages, but it is so beautiful that I like to repeat it. Not to forget anything. Well, I'm going to define a few things, and at the end, the result will be clear. So now, assume we have our finite automata. S is a set of states. Okay, zero initial state, delta a certain transitive function, and tau output function. Now I will just set a number of definitions. First, I define a number of integers such that, with the following property. These are the such positive integers that if I send binary expansion of them to the input of my automaton, then by applying my transitive function delta, by functioning automata on this input, I will arrive at the end to the state S. One more time, K is exactly the set of inputs such that automata terminates at the state S. Then, with this set, I define the function f s0s. It is simply a generating function of this set. Not, well, kind of. Z to the k. Pretty simple. Now a small remark. If I consider all such functions, then the function I'm looking for, such that at the point 1 over 10 it will give me my automatic number, will be the following function. F of u will be a finite linear combination, just a sum over states of these my functions. I have to sum up them with the coefficients equal to the output function. Well, my variable is z, so it will be z here as well. Now, if your automata constructs alpha, this function f exactly satisfies the property f of 1 over 10 is equal to alpha. And now we can easily describe the functional system for this function. Well, I pick up an arbitrary function from this class. I mean, for a fixed arbitrary s. I say, okay, now I sum up powers z to k over all such k that we terminate at s, if we send this input. Now I rearrange all the terms according to the state I had exactly before the automata terminates. According to the state, I had exactly one step before the end of work. So I will denote this, so to say, second from the end state as s prime. I sum up over it, because a priori it could be any state. Then a priori I could arrive to my final state s by applying any digit. I take all the digits from 0 to q under the condition that these digits send me from well, they send me to s from s prime if I apply if I send the digit to my automaton. Well, and here I have to put the sum of all the inputs such that with this input I go from S0 to my state which precedes the terminal state. Well, it's just a simple combinatorial equality. Now I can remark that this is nothing but f s0 s prime, where I substitute z to q instead of z. I keep two autosums. And here I have f s0 s prime of z to q. Yeah, I have to put that to L to make the equality correct. Well, now this is just a finite sum, like that. So I can denote it by a s prime s of z. This is a polynomial. And what is written down here is a Mahler type system. Oof. So this is a proof of this funny effect, just stated here. So now I recall you that finally historically it appeared later than this theorem was proved. But for solutions or for functions which satisfy this functional system of equations, we have all the needed transcendental results. Yeah. Yeah. Basically here, first of all, for them, we know that this function is either rational or transcendental. Then it is pretty recent result, actually this year result, that all the relations between values of functions are precisely the relations between functions themselves. So, for example, function f1 takes, for example, algebraic values if and only if f1 is algebraic. But it happens only if f1 is rational. And so in the case of our system of polynomials, which we constructed here, if the value of f1 at 1 over 10 is rational, then the function is rational itself. Finally, this result, it proves, well, it reproves the result by Adamczewski and Bourgeois. However, it is more strong because it is hidden in the calculations, but whilst all the automatic sequences all the automatic numbers, they can be produced in this way. But actually, if you take Mahler systems and simply pick up a function f1, calculate it at point 1 over 10, the class of numbers that you find is much larger than the class of automatic numbers. You find a lot of other things there. The question is that now, well, there are many questions we can ask. First of all, these numbers that we find just in this way corresponds to something in terms of machines of other types, of some machines with memory. What are these machines? Moreover, as I have told, we can allow here much more complicated substitutions that to Q. Again, it corresponds to some machine. We could even ask, well, maybe occasionally these Mahler systems somehow describe all the cases of Turing machines which do calculations in linear time. However, that appeared to be not true, which is not a big surprise. It's not this result which shows it. Well, it is this third result. It is not published yet. Well, Bell, Bourgeois, and Kuhn, they showed that Mahler number cannot be a Liouville number. So in particular, the Liouville constant, which can be produced in linear time, can't be described by the means of that system. Still, well, there are some restrictive results. Again, if we allow here more general substitutions, there is no this result. Actually, we can produce some Liouville numbers in this way, but maybe there are some restrictions the other way. This again, just one more result. It appeared also that Mahler number cannot be either a U number. Not only it can't be approximated too well with rationals, but it can't be approximated too well with any algebraics, whatever this too well means. Now, in the last 5 minutes, I would like to speak about that problem in algebraic dynamics, which I'm interested in. Well, if you remember these calculations with Mahler's constant, which I did in the very beginning, well, what we did, we constructed basically a trivial functional approximation to our Mahler's function. We constructed this polynomial Pn. Is it still here? Or? Yeah. just element of the proof. We first constructed this Pn, which had sufficiently big order of vanishing at if you substitute z and a function. Later it was Mahler's function. Then we started to substitute z to square, z to 4, z to 8, and so on there, moving from a trivial approximation order, which we can assure for any analytic function here, to a non-trivial approximation order, which finally allowed us to conclude. And at the final stage, we just substituted a number, and it appeared that a nice functional approximation allows us to obtain nice rational approximation, which finally allowed to conclude that this number is not transcendental. In fact, improving such kind of theorems, calculations are more complicated, but the idea basically is the same. I'll try to write here. Well, of course, it is not enough now to produce just one polynomial with very good order of approximation. If you want really a result about transcendence degrees, that to say, for example, how many algebraic numbers formed here can be independent between them, we need to produce series of polynomials. And such series of polynomials that the corresponding hypersurfaces, they intersect properly. That to say, we can't take the multiple of the same polynomial. So in this problem, we, for example, in the setup of theorem of Nishoka, we need, say, sequences, something like polynomials in many variables. I mean, it should be sequences. With high vanishing order. At basically at f of z. In fact, what we could do, we could construct just one approximation and then start to iterate by substitutions. We imagine we again start with just one polynomial. Which has big order of vanishing at 0 to some v of n, where v is approximately of the order n big to the power n small. And then we could start substitute z to d to k. And then apply to these terms this functional equation. What we would expect in general, say, not even heuristically, but from the common sense, is that the polynomials which we will find, they will intersect properly with our initial polynomial. So in this way, we can construct a nice sequence of polynomials with good properties. But to assure this, I need the following statement. In fact, well, if you got lost by this moment, I'm sorry, you can forget it and just listen to the statement of the problem. I tried to explain in a couple of minutes why it's linked to that system. Well, it is not very I state a concrete problem, but I'm interested in any positive result around this. Say, assume that you have a morphism phi from Rn to Rn. And assume this phi is well, locally invertible. And algebraic. Algebraic, at least for me, means that it is given by polynomials. Dominant. That to say preserve dimension in the common position. Or you can replace it with, it is onto. Then, now fix a certain set of transcendental functions. For example, Mahler functions. Fix f1 of z, fn of z, a set of Mahler's functions.
Dominant like x square or?
Well, I just try to simplify a certain problem. Let's say on. Yes. I'm sorry to change the conditions all the time, but well, the original problem is about something in projective space. Just say it is subjective. Set of Mahler's functions. That to say that this system of functions is a solution to the linear system we have seen. Yeah. Now, we want to consider a class of varieties which are stable under phi. That is to say, which map to itself by phi. The class, say, C phi of algebraic varieties in R. Again, here algebraic varieties means everything you can cut with polynomials and maybe just taking one irreducible component out of it. X such that phi of x is mapped, is mapped to x. For example, if you consider only varieties of one point, that will be stable points of phi. And now the question is the following. The last definition, in fact, for all such subvarieties, I'm interested in to measure something like a distance from x to this set of functions. The easiest way to do this is simply define, say, d from f to x by minimum for all the polynomials in n variables, with integer coefficients, such that p vanishes on x. I will add some, well, I add exponential here in the beginning. Here, what I consider in this minimum, I evaluate p at point f1 of z, fn of z. Take order of vanishing at 0. I calculate the order of tangency of p. e to the germ of this function. And to make it really distant, I think I have to take exponential of minus this. Exponential of minus this. It might look complicated, but I consider simply all the polynomials which pass by my variety, and among them, take the one with the least order of mention at the given point, at this set of functions. Now the question, is it true or false? Or rather, question? In fact, I'm interested in positive answer. So the question will be like this. Describe the situations presumably it will be almost all the situations when the distance defined like this from f to my variety x is lower bounded by certain constants for all stable varieties. For all x from well, there are some degenerate situations, as far as I remember, something like rotation. But say for sufficiently general morphism, it has to be true in this version. Thank you for your attention.
Any questions for Evgeniy? Okay, if there is no questions, we can move on.